Okay, now let's move on to pH. Yes, we're going to get this graph in your notes and label it correctly. So quit rolling your eyes, sighing, shaking your head, and pursing your lips for Pete's sake. So let's look at what this graph tells us. So let's look at now the pH ranges in this graph. So we're going to look at it relative to the digestive system. Okay? So here's pepsin. We've heard of pepsin before. Pepsin is the one of the enzymes that works in your stomach, and you can see what range it works in from 0 to about 4.5 or 5. So its optimum range is very acidic. Then there's trypsin, which works in the large intestine, small intestine rather, and its range is on the other end, which is basic, somewhere between 6 and 11. And then you see this hump right here, which is neutral, right around 7. So examples of pH, lower pH enzymes and higher pH enzymes. So they work in quite a range of pHs. So each of these would have its own optimum pH. Now, let's take a closer look at what's going on here with these lines. We know the shape of the lines. We've seen them before. So you can probably make a pretty good guess about what's happening now to the enzyme as that, for example, as this pH starts to get higher and higher, it works better in this 2 to 3 range until it gets to this point, and then something happens to it. So this graph is really showing us that enzymes can work in many different pH ranges. Write in your notes that changes outside the optimum pH range mean adding or removing hydrogen ions, which again disrupt the bonds that hold the enzymes together. Remember the word we used to describe this? Yes, the enzyme denatures or loses its shape. You know what happens then, right? Ultimately, the reaction rate decreases as more of the enzyme gets denatured. Write in your notes that pH mainly affects the secondary and tertiary structures of a protein by disrupting the attractions between charged amino acids. Remember, proteins have folding, and we call those folding structures primary, secondary, tertiary, and quaternary. Well, enzyme affects the secondary and tertiary structures. Now, as far as optimal pH goes, that really depends on the localized conditions. For example, we talked about pepsin working at a low pH between 2 and 3, and trypsin working in that pH range of about 8. Now let's talk about salinity or saltiness. That's why they call crackers saltine crackers, because they have lots of salt in them. So yes, get this graph in your notes and don't complain about it. Then write in your notes that changes in salinity either add or remove cations and anions. Now this removal of cations and anions disrupts the peptide bonds and the 3D shape of the enzyme. So in your mind you're going, okay, that's called denaturing. Right, that's exactly right. Also write that it disrupts the attraction between charged amino acids, once again affecting the secondary and tertiary structures. All of those denature the protein. Once that protein's denatured, the binding site changes shape and it can no longer bind with its substrate. The bottom line here is that enzymes are very intolerant of extreme salinity. The Dead Sea is called the Dead Sea, and it's dead for a reason. Okay, now on to a class of compounds which actually help enzymes do their job. Write in your notes that enzymes that help, or that compounds that help enzymes do their job are called activators. So we're first going to talk about an activator called a cofactor that you see here. Write in your notes that cofactors are small, organic, non-protein molecules that carry chemical groups between enzymes, and that cofactors are sometimes referred to as co-substrates. Co-substrates, which gives us a clue as to their function. Also write that these molecules are substrates for enzymes and do not form a permanent part of the enzyme structures. Now, it's this that distinguishes cofactors from what are called prosthetic groups, which are non-protein components that are bound tightly to enzymes like iron, sulfur centers, flavin, those kinds of things. Both cofactors and prosthetic groups are types of a broader group of cofactors, which are any non-protein molecules that are required by an enzyme for its activity. So get that down in your notes. Also write that in metabolism, cofactors are consumed and recycled continuously, with one set of enzymes adding a chemical group to the cofactor and another set removing it. For example, enzymes such as ATP synthase continuously phosphorylate ADP, adenosine diphosphate, converting it into ATP, while enzymes such as kinases dephosphorylate ATP and convert it back to ADP. Now that's a mouthful, but it's a mouthful you need to get in your notes. So if you got to go back and write it correctly, do so right now. Okay, now on to coenzymes. Write in your notes that a coenzyme is a non-protein organic chemical compound that is bound either tightly or loosely to an enzyme near its active site and is required for catalysis. They can be considered helper molecules or ions that assist in biochemical transformations. Certain substances such as water and various abundant ions may be bound tightly by enzymes but are not considered to be coenzymes since they are ubiquitous, meaning they're located all over the place, and rarely limiting. Some sources limit the use of the term coenzyme to inorganic substances. Get in your notes that coenzymes are often vitamins or made from vitamins. Many coenzymes contain nucleotide adenosine as part of their structure, such as ATP, coenzyme A, NAD, which we'll talk about. Those are all things involved in photosynthesis. And that this common structure may reflect a common evolutionary origin as a part of ribozymes in an ancient RNA world. So get that down in your notes. I know that's complicated. I get that. If you got to go back, you got to go back. But these have both appeared on the AP exam, so we got to get them in your notes and you got to get them in your head. Now, even as specialized as enzymes are, even they need to be regulated. Let's list some of these regulators in your notes, and then look at some ways they are used or are accomplished in living organisms. So write these 4 ways enzymes are regulated that you see here: competitive, non-competitive, irreversible, and feedback. And then we'll go into some detail about each. First is something called competitive inhibition. Write in your notes that competitive inhibition is a form of enzyme inhibition where binding of the inhibitor to the enzyme prevents binding of the substrate and vice versa. Now you see it right over here on the right-hand side. You see it. Now here is the normal substrate. That's why it has an S on it. And here's the inhibitor. So when an inhibitor, this molecule then gets into this active site and prevents the substrate now from binding to the enzyme. Also write that in competitive inhibition, the inhibitor binds to the same active site as the normal enzyme substrate without undergoing a reaction. Therefore, the substrate molecule can't enter the active site while the inhibitor's there. And the inhibitor cannot enter the site when the substrate is there. In this case, the maximum speed of the reaction is unchanged. So again, it's called a competitive inhibitor because it's competing now for this active site. So sometimes the substrate wins, sometimes the inhibitor wins. However, in your mind, you ought to be thinking to yourself, well, if there's an inhibitor present, it should shift now my reaction line down. The reaction line itself is not going to look any different. However, the total rate of reaction, or the amount of times the substrate binds, to the enzyme would actually decrease. If the binding decreases, then the reaction rate would also decrease. Now, a good example of a competitive inhibitor is the antibiotic penicillin. Write in your notes that antibiotics, and in this case penicillin, are used to treat and prevent bacterial infections or outbreaks. And that it accomplishes this by blocking the enzyme active site that bacteria use to build cell walls. So make sure you get that down. Now, ethanol, or ethyl alcohol, is the alcohol generated for bacteria for things like beer and other alcoholic beverages. Write in your notes that ethanol is metabolized in the body by oxidation to acetaldehyde, which in turn further oxidizes into acetic acid by the aldehyde oxidase enzyme. Now, normally the second reaction is so fast that the acetaldehyde does not accumulate in the body. Now, drug companies have developed a drug called Antabuse, A-N-T-A-B-U-S-E, chemical name disulfiram. Doesn't really matter, you just be able to use the example if you're ever asked about it. Now, this causes the accumulation of acetaldehyde. Remember, normally it doesn't accumulate, but with this drug it causes the accumulation of acetaldehyde. Now, here's the reason it works. It causes an unpleasant side effect of nausea and vomiting. So for those people trying to get off of alcohol, the addition of this Antabuse causes them to get sick when they drink it. Now, this drug is sometimes used to help people overcome the drinking habit. So get in your notes that these competitive inhibitors can be treated by simply flooding the body with substrate or saturating it so it outcompetes the inhibitor for the active site on the enzyme. Let's give another example. Another example is methanol, or methyl alcohol, also referred to as wood alcohol. Now, write in your notes that wood alcohol poisoning occurs because methanol is oxidized into formaldehyde, yuck, and formic acid, which attack the optic nerves, causing blindness. So if someone were to ingest enough methanol, they could become blind. Now, also write that as a treatment, ethanol is given as an antidote for methanol poisoning because ethanol competitively inhibits the oxidation of methanol. Ethanol is oxidized in preference to methanol, and consequently the oxidation of methanol is slowed down so that the toxic byproducts do not have a chance to accumulate, and then a person does not become blind, which is a good thing. Okay, that's it for part 5. I know we're rolling here. Take a picture of your notes, submit them to Moodle, grab that study guide, and I'll see you for Enzymes Part 6. Bye.